Use of supercapacitor in Pmsm drive for electric vehicle application. Abstract. As the demand for electric vehicles are increasing, the energy usage from the battery needs to be efficient in order to achieve maximum distance on a single charge of battery. In this paper, the effective use of supercapacitor in electric vehicles having a permanent magnet synchronous machine drive is analyzed. The permanent magnet synchronous machine drive is speed regulated for motoring and braking action. The simulated results on state of charge of the battery with and without the use of supercapacitor is compared. Keywords: regenerative braking, permanent magnet synchronous machine, PMSM, drive, supercapacitors, electric vehicle, EV, state of charge, SOC. Introduction. The growth of electric vehicles industry increasing day by day due to EV's greater efficiency, less emission, low noise level and no oil fuels required when compared to combustion engines. The battery holds the significant role in improving the performance of the EVs. As it is the main source of energy that drives an EV, due to which need for reducing electrical losses and quick charging of battery is being developed. The performance of the battery can be improved with the means of battery management systems, helps in increasing the distance coverage of EVs on single charge 3.5. The use of electric drives has an advantage that it can also be used as an electric generator, hence utilized for regeneration of energy during braking 4.6. Electric power can also be generated by other forms, such as solar photovoltaic cells installation on top of the vehicles and also by the use of micro-wind turbines. Due to the fast charging and discharging period, energy storage device like supercapacitors are used with the help of a hybrid energy storage system. 1. The supercapacitors have low energy density and high power density, enabling the use of these devices more handy. The stored energy can be utilized during the peak demand for current, such as building up of initial torque. 2. Rajashekar J.S. Department of Electronics and Instrumentation. Dayananda Sagar College of Engineering. Shavij Maleshwari Hills, Kumaraswamy Layout. Bengaluru 560078, India. Fig.1 Block diagram representation of the Pmsm system. In the Fig 1 shows the block diagram representation of supercapacitor-based Pmsm drive system with regenerative braking system. In the normal drive mode, battery bank provides the necessary power to drive Pmsm motor through a DC/DC converter. Regenerative braking method is used, decelerating to reduce the speed and also bring the vehicle to a halt. The Pmsm drive acts as generator and the energy which is generated is stored in a supercapacitor bank during regenerative braking. A different DC/DC converter is used to convey the energy from Pmsm drive to the supercapacitor bank. The stored energy in the supercapacitor banks are utilized during the initial high torque building phase of the Pmsm drive, when the motoring action is started from the EV's halt position. The battery supply is only used for powering the motor after and not utilized during the initial torque building phase. But, if the supercapacitor has an energy density less than 20%, then battery is even used as the supply for the initial torque building phase. 3. Control strategy. The control strategy used to drive the Pmsm machine is a pi controller in order to control speed of the EV. The error signal of desired speed and rotor speed is given as an input to the pi controller, which outputs a current reference value. Depending on the current reference, rotor angle, and rotor current values, PWM pulses are generated. The pulses are fed to both the DC/DC converter depending on the mode of operation. 2 switches are connected from battery and supercapacitor to the DC/DC converter, one namely SBAT and SSC switches respectively. During motoring mode, the switch SBAT is turned on and the switch SSC is turned off. The power to run the motor is only powered by battery during this mode. During regenerative braking mode, the PWM of pulses are provided to DC/DC converter too. Both the switches SBAT and SSC are turned off. The Pmsm machine generates power and the energy is stored in the supercapacitor banks in this mode. During accelerating mode, the switch SSC is turned on and switch SBAT is turned off. During this mode only supercapacitor banks provide the power to the Pmsm machine to perform motoring action. The simulation first carried out without the use of supercapacitor bank. In order to carry out this scenario, the battery system is only considered for driving the machine. The current drawn from the battery is shown in the Fig 4 waveform. The Pmsm motor is brought to a halt using regenerative braking mode from 13th second to 14th second, and then acceleration mode from the 14th second onwards is executed. Since supercapacitor bank is not connected to the system, battery is used to supply the energy by turning on the SBAT switch even during acceleration mode. The current required for the motor to accelerate reaches peak high value during this period. For simulation and analysis, the simulation is executed in MATLAB/Simulink as represented in the Fig 2 for all the modes of operation. The following specification are considered for the model simulation. A Li-ion battery having 96V, 30Ah, 100% SOC is considered. Motor having a maximum power rating of 350W and torque 10 Nm. The supercapacitor of 25F is used for simulation. The simulation is carried out with and without supercapacitor connection. The Fig 3 shows the current waveform of the Pmsm drive where all the three modes are carried out. The time period between 13 to 14 second is the regenerative mode, time period between 14 to 15 second is the accelerating mode, and rest of the time period is the motoring mode. Fig 4 current waveform of the battery without supercapacitor. The Fig 5a shows the current waveform of the battery when supercapacitor bank is connected. The supercapacitor provides the energy to the motor for a duration of 1 second between 14 to 15th second. The battery supply is cut down during this period as it is in the accelerating mode, switch SBAT is off and SSC is on. The peak demand of the Pmsm drive is handled by the supercapacitor bank. The current waveform of the supercapacitor bank during acceleration mode is shown in the Fig 5b. Fig 5a, current waveform of the battery with supercapacitor. The comparison between the F system with and without the use of supercapacitor is made based on the SOC of battery. The simulation is conducted for a sample period of 100 seconds with SOC of battery at 100% initially. All the three modes motoring, braking, and acceleration is carried out on a repetitive sequence, and the simulation pattern remains same for both the system with and without the supercapacitor bank connection. The Table 1 represents the SOC of battery with and without supercapacitor bank connection to the system. The SOC of battery without the supercapacitor is shown in the Fig 6a. Similarly, SOC of battery with supercapacitor is shown in the Fig 6b. Table 1 comparison of the systems. V conclusion utilization of supercapacitor for Pmsm drive has been discussed in this paper. The simulation results are the comparison between battery energy with and without supercapacitor bank. The stored energy during regenerative braking in the supercapacitor is used during the acceleration of the EV from the halt position as it requires huge value of current. The SOC of the battery increases by 0.021% for the test duration of 100s, due to the utilization of supercapacitor. It can be concluded that the life of the battery increases, as the current from the battery to the motor for acceleration is avoided. Hence, the charge on the battery is also increased on a single charge, resulting in increase in distance coverage of EVs.